Okay, so this is the, I'll call this, what do you want to call it? Lab practice unit 1. I'm going to go through these quickly. Don't have a lot of time, but I just in case, you missed something in the lab, we can go through it and make sure you have that, and so you have the recorded video. Okay, so two uncharged conducting spheres, A and B, rest on insulating stands and are in contact. A positively charged rod is brought near A, as suggested in the figure. While the rod is in place, someone moves B away from A. How will the spheres be charged, if at all? Well, because this positive charge rod is nearby, electrons are going to flow to that side, right? There's no net charge here, but the electrons can move around. So they're going to move over here, and then this is going to be negative over here. But these are in contact, so these electrons can be pulled over here as well. All right? So the electrons are being pulled from both spheres towards the positively charged rod. What that means is when you leave the rod there, so this is positive, and you move the other one away, all the negative charge that came from this stays there, and then that leaves this as positive. So A will be negative and B is positive. Let's see, negative, positive. Your test is not going to be multiple choice, by the way. I'm sure you know this. All right, so at which points or points on the electric field is the electric field 0? Okay, so if you picture the electric field, you know that a positive charge and a negative charge is going to look something like that. It's going to point away from the positive charge towards the negative charge. So I'm going to define 3 different sectors, if you will. One is in the middle, and this is, let's just say this is Q1 and Q2. So this is going to create, electric fields are vectors, they add as vectors. So E1 is positive, this is a positive charge, it's going to point, the field is going to point away from positive charges, so E1 is in that direction. The electric field is going to point towards negative charges, so E2 is also going to point to the right. Okay, let's come over here then. In this case, E1 is going to point away from this because this is positive, and this is negative, so the field points towards a negative charge over here. Let's do the same thing over here. Field points towards a negative charge, and the field points away from, oh wait, this is E2, away from the positive charge. So right now, we can eliminate one place as a place where the electric field cannot be 0, and that is in the middle, because the two are always going to point in the same direction, so they will always add together. They will never cancel. Now then you have this side and that side. Now the problem is they are of different magnitudes, 4Q and negative 2Q. So the issue here is that even as you come closer to this charge, okay, so the electric field is equal to KQ over R squared. As you come closer to this charge, the electric field is going to blow up, right? Because if this is R and this is field strength, it's one of our R squared law. As you get closer, the electric field blows up. The problem is you're still way far away from this one, and compounding it all, this has twice the charge, so already the field is going to be twice as high from this one. So you will never be able to cancel out this field with this charge being on this side. If you look over here, in this case, as you get closer and closer to this charge, yes, the field from this goes up, but it needs to increase to cancel out that that higher charged particle over here. So whereas, I'm going to put 2 things on the same graph, R and Q. So as you move closer, the electric field, let's say this is from 1, and this is from, well, no, let's not say that. Q, and this is R. So at a fixed Q, like let's say this is, twice the charge here. As you get closer and closer, there's going to be some distance where that added charge is negated by the proximity to the smaller charge. I hope that makes sense. Okay, you'll definitely see something like this one again. A particle comes in, moving in positive x direction. There are two particles actually that have the same mass, and they have charges +3 and -2. Well, electric field, and it got cut off, but the electric field is downward, so we know that the positive charge moves in the direction of the electric field, and the negative charge moves opposite to the electric field. Okay, so one of these has to be 3, and one of these has to be 2. All right, because they're going to experience a force, so they're going to bend. Well, that means only this can be +3 and that can be -2, just because the curvature has to be greater for the higher magnitude charge. So if I were to circle this one, well, they have the same curvature. That can't happen because they have different charges. The curvature of the positive charge has to be greater than that of the negative, just because it's a higher magnitude, 3 versus 2. Okay, 2-point charges A and B lie along a line separated by a distance L. The point X is the midpoint of their separation, this is the midpoint, so this is L over 2 and this is L over 2. Which combination of charges would yield the greatest repulsive force? Well, to have a repulsive force, they have to have the same charge. So that is gone, and so is that one. Now let's look at the force as given by Coulomb's law, Q1, Q2 over R squared. We don't care about R because it's the same. It's the same distance to A as B, and we don't care about K either. All we care about is this product Q1, Q2. In this case, the product is 8. I'm ignoring the signs here because it's absolute value. In this case, well, we already scratched that out. And this is 4, and this is 7. So -2 and -4 produce the largest charge. The difference between the two charges doesn't matter. If it was -4 and -4, then it would be even higher because the product would be 16. So let's see, a small sphere of that mass carries a total charge of that. The sphere hangs from a silk thread between two large parallel conducting plates. The excess charge on each plate is equal in magnitude but opposite in sign. If the thread makes an angle of 30 with the positive plate, what is the magnitude of the charge density on the plate? Okay. I don't have nearly enough room here, but I'll start. Okay. So we've got to sum up all of our forces. We have tension, this is theta, and tension is going to have Ty and Tx components. And we also have, this is a positive charge, so it's going to be pushed this direction. We have Fe. Third makes an angle. Okay. So what we can immediately say is that all these forces cancel each other out. We also have Fg, sorry. So the sum of the forces, I like to make a chart, Y. In the x direction, I have F3, that's supposed to be Fe. And I have negative Tx, which is negative T, I have T sine of theta. Okay, so those are the two x components. And the y component, I have positive Ty, and I have negative Fg, which equals negative m times g. let's see, I'm going to have to solve in the y direction in order to get tension to put over here. So Ty, I forgot to mention this, is T cosine theta. And I can say the sum of the forces in the y direction, first of all, it equals 0 because everything is static. So T cosine theta minus mg equals 0. So T equals mg over cosine theta. Now I can come over here and say the sum of forces in the x direction then is equal to the electric force minus Tx, which is T sine of theta, and we know that equals 0 because that is also at equilibrium. So then I can say Fe equals T sine of theta, which equals mg sine of theta over cosine of theta, which is tangent of theta. Hold on to that. But I'm also going to say that the force we know is equal to Q times E. And that is mg tangent of theta. Okay. But I know E is equal to the charge density of a capacitor over epsilon naught mg tangent of theta. And I knew to go there. That's where I was headed just because that's what it asked for. It asked for the charge density. That's the only equation we have with the charge density in it. So the charge density then is equal to Q mg tangent of theta over wait. No. Epsilon naught over Q. And you can plug in the numbers for yourself. All right. Completely ionized beryllium atom, net charge plus 4e is accelerated through a potential difference of 6 volts. What is the increase in kinetic energy of the atom? Now, this is something that I didn't spend much time on because, you know, we talked about how 1 electron volt is a unit of energy. We didn't talk much about it. But we do know that we have some electric potential energy, and then at the end we have kinetic energy, and then probably, you know, electric potential energy as well. So I can say the change in electric potential energy equals the change in kinetic energy, because we're converting electrical potential energy into kinetic energy, and so then I can say this is equal to Q delta V, just because I know that's the definition of electrical potential energy. So the change in kinetic energy is Q, which is 4E, times delta V, which is 6.0 volts. So that equals 24 eV. Okay, so now you see where electron volts comes from, 24 eV. That's your answer. Okay, so in this problem, 2-point charges are located at 2 of the vertices of a right triangle. If the third charge is brought in from infinity and placed at the third vertex, what will the electric potential energy be? So what I'm going to do is I'm going to find, let's call this 1 and 2. Let's say the potential here is V1 plus V2, and then I can use that to find electric potential energy. And potential is just a scalar, so we can work with that pretty easily. We know V equals V1, which is K Q1 over, I'll just say R squared, R1 squared, plus K Q2 over R2 squared, which equals K, and this is going to be negative Q, over R1, which is square root of A squared plus B squared, because that is the hypotenuse here, A squared plus B squared, because we want the distance to that point. Let's see, plus 2Q over b squared. And there's a k in there. So when we want to find the electric potential energy, we know that is just equal to QV, so that's equal to QK. I can reverse these because one of them's a, you know what, I'm not going to. The negative Q, actually, I'm going to pull out the third charge of whoa, I made a mistake here. So electric potential energy is Q times V, but the charge we're bringing in right here is negative Q, so it's going to be negative Q. I wish they'd use capital Q so you could, you know, differentiate, but whatever. Q times the potential, which is, I'm going to pull out the K, and I'm going to pull out another Q, because there's a Q in each one of those. So it's negative 1 over square root of a squared plus b squared plus 2 over b squared. So the important part is just knowing that you can add the potential of 2-point charges by, you know, the magnitude of the charge and the distance away from that point. And then the electrical potential energy is just the charge of whatever charge you're putting at that point times the potential at that point. All right. This next one, I'm definitely going to need some extra space to do. So we want to determine the magnitude of the field at point P. So let's first just look at it for a little bit. The field from that positive charge is going to point in that direction. We'll call that 1 and 2, so this is E1. And the field from this charge, which is negative, is going to point in that direction, E2. So that means your total E is going to be in that direction. All right. So then, the magnitude of E1 is going to equal KQ over R1 squared. And that's KQ1, which is positive capital Q, so that equals K positive capital Q over R1 squared. Let's just call it R because it's going to be the same for no, yeah, well, I'll call it R. So I'll call this R. And then that's going to be R2. The problem is, and you know this is going to be exactly the same thing, so this is E1. E2 is going to have magnitude of KQ over R squared, but it's going to be at an angle, and these are vectors. We can't just add them like scalars like we can with potential. We have to add them as vectors. So I'm going to look at E1 first, plus X. This goes E1, and I can label this theta, and I know that's theta too. Just because anytime you cross two lines, theta, the opposite angles are the same. So then we have E1y and we have E1x. E1x is equal to E1 cosine of theta, and E1y is equal to E1 sine of theta. Don't worry about theta yet. We know we can find theta because we have the two legs of the triangle, but we're going to leave it like that for now. We also know that we're going to say E1y, we're going to say that's negative because it's pointing downward. So I'm just going to put that negative sign in there. All right. Now I'm going to look at E2. And let's see, I know this is theta. So that is theta, and this will be theta as well. Because it's the same angle, right? I mean, all these dimensions are the same. We said this is theta, and that is theta. So that's going to be theta, right? And that's going to be theta. right? Right. Okay, so we have then E2, E2y, and E2x. E2x, we're going to say is negative E2 cosine theta, because it's in the negative direction. And E2y equals negative E2 sine theta. So the sum of fields in the x direction is E1 cosine theta minus E2 cosine theta, or E1 minus E2 times cosine theta, where E1 then is KQ over R squared minus E2, which is KQ over R squared. Oh, would you look at that? That is 0. So the x dimension of the field is 0. The sum of the fields in the y direction then is negative E1 sine of theta plus negative E2 sine of theta, which is sine of theta times negative E1 minus E2, which is sine of theta times negative E1, negative KQ over R squared, minus E2, which is KQ over R squared, which is negative 2 KQ over R squared times sine of theta. What is theta? Now we have to worry about that. So the sum of direction in the y direction equals theta is, so let's see, this is 1 and 4. 1 meter is 4 meters. Yeah. And this is theta. Sine of theta equals opposite 1 over hypotenuse, 4 meters. So it equals 0.25, or 1/4. 1/4 times negative 2KQ over R squared. This one's kind of a beast. It takes a while, but it's not too bad. I wouldn't spend too much time on the vector stuff because it's just a repeat from stuff last year, so it's not a whole lot to learn. Determine the electric potential at point P. Okay, well, let me look at this. So determine the electric potential at point P. Okay, well that's easy because they're scalars. So V1 is just KQ over R, which is K plus capital Q over R, which, well, I'm going to leave that as R because it's the same for the other one. And V2 is K negative Q over R. So the total potential is V1 plus V2, which equals KQ over R minus KQ over R, which equals 0. There is 0 potential at that point. How much work is required to move a 1 coulomb charge from infinity to point P? Well, we know that work is negative change in potential energy. In this case, it's electric potential energy, and we know electric potential energy is Q delta V, and we know delta V is 0, so work is 0 joules. Okay, moving on. Sketch shows cross sections of equal potential surfaces between two charged conductors. What is the magnitude of the potential difference between A and H? Well, that's easy. So delta V equals VA minus VH. It says magnitude, so it's just going to be absolute value, not going to be a big deal here. If it turns out negative, I'll just drop the negative. 200 volts minus H, which is, let's see, that's negative 400. So the change in potential is 600 volts. Pretty simple. What is the direction of the electric field at point E? So we're looking at point E. Well, we know one thing, it's always perpendicular to the equipotential surfaces, and we know that the electric field always points away from positive charge and always away from high potential to lower potential. So this side is negative 50 volts, and this side is negative 400 volts. Negative 400 volts is much lower than negative 50, so the electric field is going to point to the right. Towards G. Yeah, there you go. How much work is required to move a 6 coulomb point charge from B to F to D to A? B to F to D to A. Well, first of all, we don't care about any of that nonsense because all we care is about the final point A. So, how much work is done to move that? So work equals negative change in electric potential energy, which equals negative Q delta V, which equals negative Q final VA minus initial VB. So work equals negative Q, which is negative 6.0 times 10 to the negative 6 coulombs, times VA minus VB. So VA is plus 200 volts and VB is 0 volts. So that's plus 200 volts. And you can do the math. The work is going to be negative, and that's because the positive charge is moving to a higher potential, so something is pushing it. So the electric potential energy is doing negative work. Something is doing work on the charge, and it's not the electric force. Okay, so the electric, so for this one, this is not too bad. Q is equal to CV, and we know capacitance is equal to kappa epsilon naught A over D. So Q then is just equal to kappa epsilon naught A over D times V, and we can then solve for the plate separation is K epsilon naught A V over Q. All right, so we've got the circuit stuff. What is the equivalent resistance between points A and B? Okay, so that's where I'm going to get out a different sheet of paper here. So I'm going to label this circuit 1, A, B, where this is R1, R2, R3. And we know the voltage across 1, 2, 3. Actually, I'll bring point B out a little more to that. And there's no line in between here, so I should erase that. So the voltage across all of those is 26 volts. Now I'm going to come down here to part 2, and I'm going to start by combining these two. So 1 over R23 is equal to 1 over R2 plus 1 over R3. And I can say then that 1 over R23 is equal to 1 over 2 ohms plus 1 over 4 ohms. And if I do the math, I can throw it in my calculator real quickly. Let's see, 2, -1 plus 4, -1. that equals 4/3. I'll just leave it as 4/3 as a fraction. So R, no, not equals, because that's the reciprocal. R23 equals 4/3 ohms. So the second circuit is R1, R23. And we know what R23 is. Okay? Now we can combine those and we can say R123 equals R1 plus R23, which equals 3.0, this is a simple one, plus 4/3 ohms equals, let's see, 3 times 3 is 9, so that's 13/3 ohms. And that circuit's going to look like R123. So what is the equivalent resistance? There it is. So it's going to be about, let's see, 4.3 ohms. There it is. Okay, so how much current flows through the 3 ohm resistor? Which one's the 3 ohm resistor? R1. Okay. Well, that's pretty easy one, because we know V123 is still the same 26 volts. And we know the current 123 equals V123 over R123. So that's going to be 26 volts over, what was it, 4.3 ohms. Just 6.0 amps. Why? Because if we go back to, let's say, number 2, well, here, I'll just go back on this label. So this is I123, but it's going to be the same here, too. 123, I123, I123. So the current through the equivalent resistor is the same as the current through that. But we have to go here, because if we don't know what the voltage drop over each one of these is individually. We know the voltage drop across the whole thing is 26 volts because that's given to us in the problem, but we don't know what the voltage drop over just that is. If we know the voltage drop over the whole thing is 26 volts, and we know the resistance of the whole thing, then we can find the current through the whole thing, which is going to be equal to the current through that small part. How much current flows through the 2 ohm resistor? That is R2. Okay. Well, let's go back and find the voltage drop across this. So I'll go back to 2 and sign the voltage drop across 2,3 equals I23 times R23. Well, we know what I23 is because it's equal to I123. The current through the whole thing. And that is equal to 6.0 amps times, that was it, 4/3. Okay, so that's 24, so that voltage across 2,3 is 8.0 volts. So what that means is from circuit 2, this A, B, this is R1, and this is R23, the voltage across that, the voltage drop is 8 volts. Now we can go back to 1, the circuit drawing 1, R2, R1, R3. We know the voltage drop here is going to equal the voltage drop here, which equals the voltage drop here. So we know the voltage drop R2, V across 2 is equal to V23, and we know then that, what are we asking for? The current. So then the current through 2 is equal to the V2 over R2, which is equal to V23 over R2, with V23 is 8 volts over R2, which is 2 ohms, and that equals 4 amps. Okay, I hope those problems help. Good luck on the test.